Last time, when we discussed about linear equations of order 1, we introduced the integrating factor, or we determined the integrating factor by identifying in the equation the function p of x that will lead us eventually to the integrating factor b. Now, there are some equations where the integrating factor can be determined by subjecting the equation to some test. But for now, let us consider some equations that are simple enough for us to be able to identify the integrating factor. But to do that, we must be very familiar and must have a sound knowledge about some exact differentials, namely the differential of xy, which is equal to x dy plus y dx, the differential of x over y, which is equal to y dx minus x dy over y squared, the differential of y over x, which is equal to x dy minus y dx all over x squared, the differential of arctangent y over x, which is equal to x dy minus y dx over x squared plus y squared, and the arctangent of x over y, which is equal to y dx minus x dy over x squared plus y squared. Okay, so whenever we see an expression, say x dy plus y dx, we shall write this as the differential of xy. And we know that when we integrate this, that will be equal to xy. Whenever you have the expression, the differential xy, a convenient coefficient for this is a power of xy, say xy raised to some power n, so that when you integrate, you can apply the power formula by taking xy to the n as your u to the n and the differential xy as your du. So if ever you have a coefficient of the differential of xy other than a constant, it must be some power of xy. Similarly, if you have the differential of x over y, a wanted coefficient of the differential of xy is a power of xy raised to some power, say k, so that you'll be able to apply the power formula. Let us solve on the equation x squared y cubed plus 2 sine of 2x dx plus x cubed y squared dy equal to 0. We write this as x squared y cubed dx plus 2 sine 2x dx plus x cubed y squared dy equal to 0. Let us group the first and the last term, and we can factor x squared y squared. Factoring x squared y squared from the first and the third terms, we shall be getting y dx plus x dy plus 2 sine of 2x dx equal to 0. And we see that y dx plus x dy can be written as the exact differential of xy plus 2 sine of 2x dx. As regards to second term, we have a function of x sine 2x together with dx, and there is no problem about that. Huh? For the first term, you have the differential of xy, and it appears with a power of xy. More precisely, we can write this as xy raised to the power of 2 differential of xy plus 2 sine of 2x dx equal to 0. Since we have already set up the equation, the next step is to integrate. And integrating, we get xy quantity cube all over 3, no? Applying the power formula. And then 2 sine 2x dx, when you evaluate that, will give us negative cosine of 2x equal to c all over 3. So, as for our final answer, it will be x cubed y cubed minus 3 cosine of 2x equal to c. So that is our final answer. For our second example, let us consider the equation y, 2xy plus 1 dx minus x dy equal to 0. So let us distribute our y together with dx. That will be 2xy squared dx plus y dx minus x dy equal to 0. And we can see here the expression y dx minus x dy. What is the missing term here? The missing term is 1 over y squared, and y squared is actually an unwanted coefficient for your dx. So what we're going to do is we will divide everything by y squared, thus we'll get 2x dx plus y dx minus x dy over y squared equal to 0. Continuing, we have 2x dx plus, we recognize this now as the exact differential of x all over y equal to 0. So we have here dx with a function of x and the differential of x over y. So we integrate and we'll get 2x squared over 2 or x squared plus the integral of the differential of x over y is x over y equal to c. We can multiply everything by y, x squared y plus x equal to cy, or we can factor x and then xy plus 1 equal to cy. Let us proceed to our third example. Y x to the fourth minus y squared dx is x to the fourth plus y squared dy equal to 0. Okay, so distribute y, distribute x. That will be x to the fourth y, then dx minus y cubed dx plus x to the fifth dy plus xy squared dy equal to 0. We can group the first and the third term and factor x to the fourth. We have y dx plus x dy. Next is we group the second and the last term, and let us factor y squared. So factoring y squared, let me start with the last term. That will be x dy. And then for the second term, factoring y squared will give us negative y dx equal to 0. Okay, for y dx plus x dy, we see that this is the exact differential of xy. While in here, x dy minus y dx, we need to have x squared in the denominator. What we will do is we will divide by x to the fourth. Okay, divide by x to the fourth. And then what I'm going to write here is y squared over y squared. Sorry, it should be x squared. And then x dy minus y dx over x squared equal to 0. Okay, so my x to the fourth is split into 2, x squared times x squared in the denominator. And why are we doing that? In order to complete this part, which is the exact differential of y over x. So for the first two, that is the exact differential of xy plus y squared over x squared can be written as y over x quantity squared, and x dy minus y dx over x squared is the exact differential of y over x equal to 0. Continuing, we now integrate because the coefficient of the differential of y over x is the power of y over x. No? So we can apply here the power formula. For the first one, the integral of the differential of xy is of course xy, and the integral of y over x quantity squared, differential y over x, which is actually in the form u squared du. No? U squared du, and the integral of that is u cubed over 3. So y over x cubed all over 3 equal to the integral of 0, which is a constant. Let us use c over 3. So that becomes 3xy plus y cubed over x cubed equal to c. Or 3x to the fourth y after multiplying everything by x cubed plus y cubed equal to cx cubed. Let us polish our final answer by factoring y. 3x to the fourth plus y squared equal to cx cubed. Okay? Another one. Say y x cubed, or let us say y cubed minus x dx plus x y cubed plus x dy equal to 0. Just like what we have done in the previous example, we shall write this as, okay, if we distribute y and then x and then factoring y cubed, what do we get? Y cubed, y dx, and then plus x dy. Alright? So we multiply y to y cubed dx and x to y cubed dy, and we factor y cubed. Or instead of multiplying, you just factor y cubed. Factoring y cubed, that will be y cubed times y dx plus x dy. For the other two remaining terms, negative xy dx and x squared dy, we can factor x. Thus, we have x dy minus y dx equal to 0. Okay? Then, y cube is unwanted, no, as far as y dx plus x dy is concerned, because we know that this is the exact differential of xy. So if ever there is a coefficient, it must be a power of xy and not of y alone or x alone. Alright? So we divide by y cube, we get y dx plus x dy plus, in this case, we will split y cubed into y and y squared. So we'll be getting x over y, x dy minus y dx over y squared. So y and y squared is still equal to y cubed, equal to 0. So the first two term is the exact differential of xy plus x over y. But what is this one? This is the exact differential of negative. No? We can transform this into negative y dx minus x dy over y squared. Alright? This is the exact differential of negative x over y. No? So we just rewrite this as the differential of xy minus x over y, differential of x over y equal to 0. We then integrate, hence we'll be getting xy minus, again, power formula. The power here of xy is 1, so x over y squared over 2 equal to c over 2. Or 2xy minus x squared over y squared equal to c. 2xy cubed minus x squared equal to cy squared. X 2y cubed minus x equal to cy squared. Okay. As for our final example, let me modify the problem. Wait, I might as well write this for a while. Let me just modify the problem. Y cubed, instead of just x, let me make it as x squared dx plus x y cubed plus x squared dy equal to 0. Okay, so this is similar to the last example, but instead of x, I change it to x squared. Let us see what will happen. So again, we factor y cubed. We'll be getting y dx plus x dy. And then in here, I shall be factoring x squared. Let me use negative, x squared. So that will be y dx minus x dy equal to 0. Right? And what do I need here? In the denominator, I need y squared. So I will take y squared from here. Okay? So what will remain here is y dx plus x dy minus x squared y dx minus x dy all over y squared equal to 0. Okay? So this is equivalent to y times the differential of xy minus x squared differential of x all over y equal to 0. At this point, we cannot evaluate yet the integral of the equation. Why? Because we see that the coefficient of the differential of xy is purely y. If ever there should be a coefficient of the differential of xy, it must be xy raised to some power k. Now, same thing can be said about the coefficient of the differential of x over y. If ever the differential of x over y should have a coefficient, it should be a power of x over y raised to some power r. Alright? So it is at this point wherein we're going to introduce an integrating factor. And our integrating factor here, okay, let me write this, introduce the integrating factor x to the m, y to the n. So if we multiply everything by x to the m, y to the m, I'll be getting x to the m, y times y to the n is y to the n plus 1. Then the differential of xy minus x squared times x to the m becomes x to the m plus 2, and then y to the n, y raised to n times the differential of x over y equal to 0. For x to the m, y to the n plus 1 to be a rightful and appropriate coefficient for the differential of xy, what should be the condition for the exponent of x and y? What must be the condition for m and n plus 1 for x raised to m, y to the n plus 1 to be a rightful coefficient or an appropriate coefficient for the differential of xy? Both x and y must have the same exponent. So in other words, m must be equal to n plus 1. Alright? So m and n plus 1 should be equal. On the other hand, if x to the m plus 2, y to the n is an appropriate coefficient for the differential of xy, the exponent of x, which is m plus 2, must equal the negative of the exponent of y, no? Because the differential of x over y is actually x y to the negative 1. No? So the coefficient must be such that the coefficient of x must be the negative of the coefficient of y. So in this case, m plus 2 must equal negative n. So with these two equations, we'll be able to find the values of m and n. Alright? So m is equal to n plus 1 and m plus 2 equal to negative n. So we replace m by n plus 1. So n plus 1 plus 2 equal to negative n. Alright? So that will be n plus n is 2n equal to negative 3. Thus, the value of n is negative 3 halves. And for m, it will be negative 3 halves plus 1. Your m is equal to negative 1 half. So, our equation will now become x raised to m negative 1 half, y raised to n negative 3 halves plus 1 is negative 1 half. Okay, let me write it down. N negative 3 halves plus 1 differential of xy minus x raised to m negative 1 half plus 2 y raised to negative n or raised to n, which is negative 3 halves, and then differential of x over y equal to 0. So this is equivalent to xy raised to negative 1/2 differential of xy minus x to the 3 halves over y to the 3 halves, or x over y to the 3 halves differential of x over y equal to 0. So the coefficient of the differential of xy is a power of xy. The differential of x over y is a power of x over y. We now integrate. So applying the power formula, that will be xy raised to negative 1/2 plus 1, or positive 1/2 over 1/2 minus x over y to the 3 halves differential of x over y, power formula, still power formula, that will be x over y to the 5 halves over 5 halves equal to c. Make it 2c. Okay, so that this will become 2xy to the 1/2 minus 2 over 5. Okay, let me make it 2c over 5. So 2 over 5 x over y to the 5 halves equal to 2c over 5, which will, I think I can erase this part now. So we can cancel all the 2's and multiply everything by 5. So that will be 5xy to the 1/2 minus x over y to the 5 halves equal to c. We do not want to see rational exponents, so let us do some more simplification. Okay, so that will become 5x to the 1/2 y to the 1/2 minus x to the 5 halves y to the 5 over 2 equal to c. Multiply by y raised to 5 halves. So 5x to the 1/2 y. Y raised to 1/2 times y raised to 5 halves, that will be y raised to 6 halves or 3. Okay, 1/2 plus 5 halves is 6 halves or 3, minus x to the 5 halves equal to c y to the 5 halves. Next, we shall factor x to the 1/2. Factoring x to the 1/2 will give us 5y cubed minus x. Take away 1/2 from 5 halves, that will be 4 halves or 2, equal to cy to the 5 halves. So we have come to the final stage. We square both sides. Squaring both sides, that becomes x, and then 5y cubed minus x squared equal to c squared y to the 5th. So that is our final answer. Okay. So kindly work on the following numbers. So work on these numbers and then we will discuss its solution later. Their solutions.